Okay, so yeah, so we talked about this class NP, and we saw that there are many interesting, useful problems which are in NP. Okay, so we looked at problems like factoring numbers or primes or finding cliques and coloring, and many of these problems have practical applications, and we saw that they were in NP. Okay, but we don't know whether they're in P or not. So, for example, we don't know whether it's possible to efficiently factor some numbers. So that's the main question we want to figure out, okay, is this so-called P versus NP problem, which is that if you have a problem which is in NP, can we be guaranteed that it's also in P, that you can solve this problem in polynomial time? Okay, so right now we don't know the answer to this. In fact, we're probably very far away from actually knowing the answer to this. Okay. But nevertheless, people have developed this machinery over the last about 50 years or so, which is designed to try to answer this question. Okay. And this machinery is called NP Completeness. Okay, so today we're going to focus on NP Completeness. And so, so NP Complete is another, so NP Complete is another set of problems. Okay, just like P is a collection of problems, and, what is this? And NP is a collection of problems. Okay, NP Complete, or NPC, is another set of problems. And in fact, NPC is a subset of the NP problems. And the subset is supposed to be the hardest NP problems. Okay, so out of all NP problems, these special NPC problems are the hardest problems. And so the reason we want to focus on these NP complete problems is that if you want to figure out whether P equals NP, okay, it's enough just to figure out whether P equals NPC. Okay, because suppose P does equal NP complete, okay, then that would mean that even the hardest problems in NP are solvable in polynomial time. And that would mean that any NP problem is solvable in polynomial time, right? Because if the hardest NP problems are doable in P, are solvable in polynomial time, then any NP problem is solvable in polynomial time. Okay, so by studying these NP complete problems, we don't have to study such a large set of NP problems. I mean, there are many, many, many NP problems. Okay, and NP complete is a subset out of all the NP problems. So we can now just focus on this smaller subset of problems. Okay, so this is why we're interested in NP complete. Okay, yeah, right. So basically, people have focused their study on these NP complete problems. And in fact, these NP complete problems are even better because, as I'll tell you about later, it's enough just to study one particular NP complete problem. Okay, so there are many, many NP complete problems as well. But if you want to figure out whether P equals NP, it's enough just to study any NP complete problem. You don't have to study all of these NP complete problems. Okay, so I'll show you later what I mean by that. Yeah, so basically, if you can find any NP complete problem which is solvable in polynomial time, okay, then P equals NP. And alternatively, if you can prove that there's any NP complete problem which is not solvable in polynomial time, then that proves that P is not equal to NP. Okay, so you don't have to study all NP complete problems. You can just pick your favorite NP complete problem and try to work on that one. And if you can show either that is in P or not in P, then you solve the entire P versus NP problem. Okay, so this is why it's nice to study these NP complete problems. All right, so before we prove that fact, let me just sort of define what all this stuff is, okay? So the first thing we need to do is, so I said that these NP complete problems are the hardest NP problems, okay? So what do I mean by hardest problem, okay? In fact, if I give you two problems A and B, okay, how can you say that one problem is harder than another? Okay, what is a mathematically rigorous way to say that one problem is harder than another problem? Okay, so for example, if I say that problem B is harder than problem A, what do I mean by that? Well, it turns out that you can define this to mean that, so what this means is that if you can solve problem B, okay, then you can also solve problem A. That's what it means for B to be harder than A. Okay, because if B is harder than A, and if you can solve this hard problem, then you can also solve the easier problem A. Right? That makes sense, right? Okay, so as an example of this, so you can say that algebra is harder than arithmetic. Okay, because if you can do algebra, then you can also do arithmetic. Okay, now the other way around might not work. Okay, so maybe arithmetic is not harder than algebra, because if you can do arithmetic, maybe that doesn't mean you can actually do algebra. Okay, so intuitively, this is what we mean when we say one problem is harder than another problem, is that if you can solve the hard problem, you can also solve the easier problem. Okay. Another way to say this is that if you have an algorithm for solving B, okay, then you can somehow use this algorithm to also solve A, which is the easier problem. Okay. All right, so I'll be more rigorous about this in the next few slides, but I just want to give you the intuition first. Okay, so when you have this easier problem A and this harder problem B, right, then we say that A reduces to B. Okay, so in other words, in order to solve A, we can reduce that to solving this harder B problem. Okay, and we have this notation for expressing that, which is that A is less than or equal to, with this R symbol over here, A is less than or equal to B. Okay, and the way you read this is that A is equally or less difficult than B. Okay, the R stands for reduction. Okay, so let's do another example of this. Okay, so suppose we have two problems. Okay, so the first problem is called factor all. So here I give you a number, and you have to find all the factors of this number. Okay, and the next problem is called factor one, which is that I give you a number, and you just have to find one factor of this number. Okay, so for example, if I give you 100, okay, you just have to tell me a factor is 2 or 5 or something like that. Okay, factor all is that you have to give me all of the factors. Okay, so obviously factor 1 can reduce to factor all. Okay, so factor 1 is easier, or at least it's not harder than factor all. Okay, because if you can solve factor all, okay, meaning that you can find all the factors of any input, okay, then of course you can find one factor. Okay, so if you can solve factor all, you can also solve factor 1. So therefore, factor 1 reduces to factor all. Okay, but it turns out that factor all also reduces to factor 1. Okay, so that means that factor all is not more difficult. Okay, it's less than or equal to in difficulty than factor 1. Okay, it's less difficult or equally difficult to factor 1. And the reason for this is that suppose you have an algorithm to solve factor 1. Okay, then if I give you an input n, you can use factor 1 to find some factor of to find one factor m of n. Okay, and then you can just take n and divide it by m. Okay, and whatever that number is, then you can run factor 1 again on that result, and that way you can find another factor of n. Okay, so you can just keep repeating this process, so you can always find a new factor and then divide it into the previous number, and that way you can get all of the factors. Okay, so this shows you that if you have an algorithm for factor 1, right, then you also have an algorithm to solve factor all. So therefore, factor all is not more difficult than factor 1. Okay, so another way to say this is that the hard part about factoring a number, about finding all the factors, okay, is simply just to find one factor. If you can find one factor, you can find all the factors. And also, because we have that factor 1 is not more difficult than factor all, and also factor all is not more difficult than factor 1, then we can say that these problems actually have equivalent difficulty. Okay, they're equally difficult to each other. Because if you can do either one, if you can do either factor 1 or factor all, then you can solve the other problem also. Okay, are there any questions about that? Does that make sense? Okay, all right, so that's like the intuition for these reductions. Okay, so now let's be more rigorous about this. Okay, so let's define this mathematically. Okay, so so suppose you have two decision problems, A and B. So remember that decision problem just means that this problem either has a yes or no answer, right? Like for example, a number is either prime or it's not prime. Okay, yeah. All right, so if you have these two decision problems, then we're going to let X be the set of yes instances of A. Okay, so for example, if A, I guess I have the example here. Okay, yeah, so if A is the primes problem, okay, then the set of yes instances is just the set of prime numbers. Okay, and the set of no instances for A is the set of composite numbers. Okay, and likewise, let's let Y be the set of yes instances for B. Okay, so if B, for example, is another problem, it's like the K-clique problem. Okay, then Y is a set of graphs which contain a K-clique. And then the set of no instances for K-clique would be all of the graphs which do not contain a K-clique. Okay, all right, yeah, so we have these A and B problems, and then we have X and Y, which are the set of yes instances for these problems. Okay, so now we have a function f which can map instances of A to instances of B. Okay, so yeah, so I'll show you sort of what that means later, or I'll give you an example of that later. Okay, but basically what happens is, you know, if I give you like, so for example, if f maps from this primes problem to the clique problem, then that basically means that if I give you any number, okay, then you can, then this f function is going to convert that into a graph. Okay, so an instance of A becomes an instance of B. Okay, so now we're going to say that problem A reduces to problem B if there is one of these mappings f from A to B, such that for all of the yes instances, so for all instances of A, okay, if this x is a yes instance, then f of x is going to be a yes instance of B. Okay, so yeah, so let me say that again. Okay, so if you have a yes instance of A, right? So x is a set of all yes instances for A. Okay, then f of x is going to be a yes instance for B. Okay, yeah, and this is an if and only if condition. So if you have a no instance of A, right, then f of x is going to be a no instance of B. Okay, so so the yes instances of A exactly map to the yes instances of B. Okay, right, and then if you have one of these reductions f, okay, if you have this f which satisfies this property, then you're going to say that A reduces to B. Okay, and we're going to use this less than or equal to notation. Okay, so so if you want to show that a problem A reduces to B, then all you need to do is to find this mapping. Okay, if you can find the mapping which has this property, then this shows that A reduces to B. Okay, and now we can say that if A does reduce to B, okay, then if you have an algorithm for B, you can use it to solve A. Okay, so that was our intuition for what it means for A to be easier than B, right? Meaning, which is that if you can solve B, then you can solve A. Okay, and so now we can show this property formally. Okay, because if A reduces to B, then in order to solve an instance of A, what we're going to do is we're going to use this function f and first convert the instance of A to an instance of B. And then because you have an algorithm for B, then we're just going to run the B algorithm. Okay, and then whatever answer this B algorithm returns, right, we're going to return the same answer for A. Okay. And this is and now this overall algorithm, okay, this entire thing, this is a valid algorithm for A. Okay, because what we know is that if we start with a true instance of A, okay, then after you do this mapping, you're going to get a true instance of B. Or a yes instance. If you have a yes instance of A, then after this mapping f, you're going to get a yes instance of B. Okay, and then so when you run this B algorithm, this algorithm is going to return yes, right? Because you have a yes instance of B. Okay, and then we're going to return the same answer for A. Okay, so that means that whenever you have a yes instance of A, we're going to return yes using this composite algorithm over here. Okay. And then if you have a no instance of A, then f of this instance is going to be a no instance of B. So when you run the B algorithm, you're going to get no as your answer. And so you're also going to return no for the A problem. And again, that's correct. Okay, so as long as you have this reduction from A to B, and you have an algorithm for B, then you can solve problem A. Okay, any questions about this? Is that a reasonable definition? Okay, all right, so yeah, so let's do an example of this. So let's consider these two problems, prime and k-clique. Okay, so what would it mean to show that prime reduces to k-clique? Okay, so what this means is that we have to find some mapping f, okay, such that if we have an instance of prime, okay, in other words, we have a number, okay, then first of all, f of n is going to be a instance of k-clique. In other words, f of n is going to be a graph. Okay. Furthermore, we have to have that if n is a yes instance of prime, so n itself is a prime number, okay, then f of n must have a k-clique. Okay, so a yes instance of prime is going to map to a yes instance of k-clique. Okay, and on the other hand, if you have a no instance of prime, in other words, you have a composite number, right? Then this has to map to a no instance of k-clique. So then this has to produce a graph which does not have a k-clique. Okay, so n is going to be a prime if and only if f of n contains a k-clique. Right, that's what it would mean to for prime to reduce to k-clique. Okay, so now suppose you have an algorithm to solve k-clique. Okay, then you can use it to solve prime. Because now if I give you a number and I ask you if it's prime or not, you're just going to use your mapping f, and you're going to map the number to a graph G, and then you're going to run your k-clique algorithm, right? And whatever answer this k-clique algorithm returns, you're going to return the same answer for prime. Okay. Yeah. So yeah. So so if you can find such a mapping, then this would show that prime is not more difficult than k-clique. Okay, yeah, so that's how we define reductions. Okay, so the next thing is we're going to define a special type of reduction, which is polynomial time reductions. Okay, because for the reductions, we didn't put any restrictions on this. Here, let me erase some of the stuff. Okay, so let me clean this up. Okay, so for reductions, all you need is that you need to find some sort of mapping f over here. We don't put any restrictions on this mapping. So in particular, this function f can be very hard to compute. It can take a long time to compute, maybe like exponential time or something. Okay, so for a reduction, we don't care how long or how much resource, either time or space. We don't care how much it takes to compute f. However, when we want to study this P versus NP problem, we actually don't want f to be very hard to compute. Okay, we want f to be efficiently computable. So this is why we're going to study polynomial time reductions. Okay, in this case, this mapping f from A to B, it has to run in polynomial time. So if you can find a reduction which runs in polynomial time, then you're going to write things like this. Okay, so A is less than or equal to B, and then you have this little p thing here to indicate that the reduction is polynomial time. Okay, so for example, if you want to do a polynomial time reduction from prime to k-clique, then your mapping function has to actually run in polynomial time. Okay, so then once you have this, so the nice thing about this polynomial time reductions is that you can compose them. So what I mean by that is, suppose you have three problems, A, B, and C, okay, three decision problems. And suppose you know that A polytime reduces to B, and B polytime reduces to C. Okay, then you have the transitive property, which is that A polytime reduces to C. Okay, so just like, the normal less than or equal to sign, right? If you have A is less than or equal to B, write that, which is less than or equal to C, right? Then of course A is less than or equal to C. Okay, and likewise for these reductions, right? We have the same property. Okay, all right, so it's pretty easy to prove this. So the proof is that since A polytime reduces to B, okay, then there is some sort of polynomial time mapping F from A instances to B instances. Okay, and also because B reduces to C, then there's also a polytime mapping, another polytime mapping, G, from B instances to C instances. Okay, so now if I have an instance, or it should be little x of A, well, anyways, whatever. So if I have an instance x of A, okay, then let's let y be the first mapping using F. Okay, and then let's let z be the second mapping using G. Okay, which is simply equal to G of F of x. Okay, so now we know that x is going to be a yes instance of A. So by the definition of F, okay, we know that x is a yes instance of A if and only if y is a yes instance of B, right? Because y equals f of x. Okay, and then by the definition of G, we know that y is an instance of B, is a yes instance of B, if and only if z is a yes instance of C. Okay, because z is equal to G of y. Okay, and so this means that x is a yes instance of A if and only if z is a yes instance of C. Okay, yeah, and so this shows that, and then if we use this composite reduction function, okay, so G composed with F, right? So you first run F and then you run G, right? So this is the compose function. Then this is a valid mapping from A to C, okay? Because both F and G themselves run in polynomial time, so when you compose them, it also runs in polynomial time, right? The complexity is just equal to the complexity of F plus the complexity of G, right? Just run one algorithm after the other algorithm, okay? So G composed with F runs in polynomial time, and we know that X is a yes instance of A if and only if G of F of X is a yes instance of C. Okay, so therefore G composed with F satisfies all our reduction properties. And so this shows that A reduces to C. Okay, any questions? Okay, so all right, so next we're going to define NP completeness. Okay, so we're going to say that a problem A is NP complete if the following two properties are true. Okay, so first of all, this problem A has to belong to the set NP. Okay, so all NP complete problems have to be also NP problems. And the second property is that if you have any other NP problem, B, let's say, okay, then B has to polynomial time reduce to A. Okay, in other words, B is somehow easier than A. Yeah, so right, yeah, so therefore an NP complete problem is an NP problem, okay, which can be used to solve any other NP problem. Because if you take any other NP problem B, right, then B has to reduce to A. So therefore, if you can solve this NP complete problem A, then you can solve any NP problem B. So that's why these NP complete problems are the hardest NP problems, okay? Because if you can solve this NP complete problem, you can solve any other NP problem. Okay, so that's the definition. Any questions about this? Any questions? Okay, all right, so So the next thing is, okay, so we said that these NP-complete problems are the hardest problems. Okay, but the question is, do there actually exist NP-complete problems? Right? Are there actually these problems in NP such that all of the other NP problems reduce to these NP-complete problems? Okay, it might be possible that there are no complete problems, right? There are no hardest problems. It could be that all of the NP problems are somehow very different from each other so that it's not possible to transform one NP problem to some other NP problem. Okay, so this is definitely a possibility. But it turns out that indeed there are NP-complete problems. Okay, there do exist these very, very hard NP problems such that all other NP problems reduce to the NP-complete problems. Okay. So this is a very famous result, and it was proved around 1970 by these two people, Steve Cook and then Leonid Levin from the USSR. So they proved that a particular problem called SAT is NP-complete. Okay. So yeah, so basically, okay, yeah, so what is the SAT problem? Okay, so SAT stands for satisfiable Boolean formulas. Okay, so Boolean formula is just something like, A or B, okay? And then A and B are Boolean variables, and then we're trying to find truth settings for A and B so that this overall formula is satisfied. So for example, if you set A to true and B to false, right, then this formula is satisfied. So the question is, if I give you a Boolean formula, does there exist a setting for the variables which makes the formula true? Okay, so for example, if you have this this Boolean formula, okay, then if you set A, B, and C to true, and if you set D to false, then this entire formula is satisfied. Okay, so this is a yes instance of the SAT problem. Okay. On the other hand, if you have like an expression like this, A and not A, right, then whatever you set A to, this formula is false. So therefore, this formula is not satisfiable. Okay, no matter how you set the variables, you always get false, and so this is not a satisfiable formula. So this formula is not in SAT. Okay, SAT is a set of all satisfiable formulas. So this one is in SAT, and then this other one is not in SAT. Okay, so yeah, so Cook and Levin proved that SAT is an NP problem. Okay, so so there's this so the result is called the Cook-Levin theorem, and it says two things. Okay, so so first of all, so the Cook-Levin theorem says that SAT is NP complete. So that means that, first of all, SAT is an NP problem. So you should try to think about, you should try to prove this fact yourself. Okay, how can you prove that SAT belongs to the class NP? Okay, and so this is going to use sort of ideas like what we talked about last time. Okay, so last time we showed how to prove problems are in NP. Okay, so so that's the first part of the Cook-Levin theorem, and this is not so hard to do. Okay. The second part of the theorem is much harder, and what it says is that if you take any NP problem, then that problem reduces to SAT. Okay, so in other words, any NP problem, A, okay, can somehow be mapped to a SAT formula phi, and you can do this mapping in polynomial time, such that if A is true, then phi is satisfiable, and if A is false, then phi is not a satisfiable formula. Okay, so that's the second part, right? Because in order for a problem to be NP complete, we need all NP problems to reduce to this NP complete problem. Okay, so we need all NP problems to reduce to SAT in order to show that SAT is NP complete. Okay, so yeah, so this is so the hard part about doing this is that this fact has to hold for every NP problem. Okay, and there are an infinite number of NP problems, right? So how can you show that something's true for an infinite set? Okay, so I'm not going to go through the proof of this because it takes a long time, but the basic idea is not too complicated. Okay, so the basic idea is that because this problem is an NP, this A problem is an NP, okay, then A has a polynomial time verifier. right? That's the definition of NP. Okay, so A has a polynomial. So there's some algorithm which runs in polynomial time which can verify yes instances of A. Okay, and now the SAT, if you look at these SAT formulas, okay, so they can be used to model any sort of logical operation. Right? And if you think about an algorithm, then basically the algorithm is just doing a bunch of logical operations. Right? If you think about your computer, okay, it's operating on bits, right? It's operating on zeros and ones, okay, which are like trues and false. Okay, and all the computation that your computer does, you can actually capture that using a very, very complicated SAT formula. Okay? Because all the computations your computer does, right, they're always done using, first of all, bits, okay, so true or false. And the only operations you need to do are these AND operations and OR operations, or these negation operations in the computer. Right? You can build any computer out of these three operations. And so therefore, you can model the entire computation your computer does using a very, very large SAT formula. Okay? And in particular, you can model the computation that the verifier, let's say that this A problem has a verifier V. Okay? So V itself is an algorithm, and you can use some sort of big SAT formula to model what the computation for this what computation this verifier is doing. Okay, you can emulate the verifier. Okay. And when you emulate the verifier, then whenever you have a yes instance of X, okay, then there's some certificate to make this verifier return 1. Right? That's the definition of the verifier. Okay. And this certificate can actually be transformed to a satisfying assignment for this formula phi, where phi is modeling the V computation. Okay, and then if you have a certificate which makes this verifier return 0, right, then this would correspond to a non-satisfying assignment for phi. Okay, so a correct certificate for V corresponds to a satisfying truth assignment for phi. And an incorrect certificate corresponds to a non-satisfying truth assignment for phi. Okay, and so that means that this phi formula is satisfiable if and only if there is a certificate to make the verifier output 1. Okay, in other words, phi is satisfiable if and only if X is a yes instance. Okay, and so therefore X reduces to SAT. Okay. And furthermore, this entire construction, this phi formula, okay, this can be constructed in polynomial time. So this is a polynomial time reduction. Okay. So that's the basic idea for how you show that any NP problem can be reduced to SAT. Okay. Any questions about this? Okay, all right, so next we're going to see why NP complete problems are useful. Okay, so I sort of mentioned this, but now let's sort of see it more directly. Okay, so we have this picture over here, okay, which is a bunch of different problems. Okay, each of these things is a different problem, like circuit SAT and so on. And then for every problem in this picture, okay, so you notice these arrows. So if A points to B, okay, then this is indicating that A polytime reduces to B. Okay, in other words, A can be solved using B. So for example, this let's see, second, yeah. So so in fact, I said that SAT was a problem that Cook and Levin proved to be NP complete. Okay, well this is not quite true. So they proved a very similar problem called circuit SAT is actually NP complete. Okay, so this was like the very first problem that was proven to be NP complete, is this circuit SAT problem, okay, up top in this diagram. Okay, now we said that in this diagram, whenever you have this arrow, it means that you know, the first problem reduces to the second problem. Okay, in other words, if you have a if you have an algorithm to solve the second problem, then you can also solve the first problem. Yeah, so Cook and Levin showed that basically any NP problem, okay, so suppose you have a bunch of NP problems, let's call them X, Y, and Z, okay, so they're all going to reduce down to SAT, okay, so they can all be solved, circuit SAT, okay, so X, Y, and Z can be solved using circuit SAT. And furthermore, because we have this arrow here, then this means that circuit SAT can be solved using SAT. And so now you can say that x, y, and z can be solved using SAT. Okay, because in order to solve x, for example, you can map it to an instance of circuit SAT, right? And then now to solve this instance of circuit SAT, you can map it to another instance of SAT. And once you solve the SAT instance, then you've also solved the instance of x. Okay, and this holds for any NP problem. So this means that any NP problem can be reduced to SAT. And so that means that SAT is also NP complete. Okay, because every NP problem reduces to SAT, so SAT is also NP complete. Okay, and now SAT can also be reduced to this other problem of 3CNF SAT. Okay, and so by the same logic, 3CNF SAT is also NP complete. Okay, and and 3CNF SAT can be reduced to these two different problems. It can either be reduced to this clique problem or the subset sum problem, right? And so again, by the same logic, both clique and subset sum are also NP complete problems. Okay, so in fact, if you just follow all of these arrows, what you see is that all of the problems on this in this diagram are NP complete. Okay, and the only thing we need to show that these problems are NP complete is that we need to establish that all of these arrows, okay, all of these things are valid. In other words, we need to establish that circuit SAT reduces in polynomial time to SAT. Okay, and you also need to show that SAT reduces in poly time to 3CNF SAT, right? And 3CNF SAT reduces to clique or to subset sum. Okay, so you actually need to prove all of these arrows are correct. Okay, each of these arrows corresponds to a reduction, and you need to prove that this reduction exists. Okay, so this is sometimes kind of hard to prove these reductions. And in fact, in the second part of this lecture, we'll look at some of these reductions to show how you can actually do these proofs. Okay. But if you can do one of these proofs, then that shows that you can put one of these arrows between these two problems. Right? If you can reduce one problem to another problem, then you can put an arrow from the first problem to the second problem. And so that means that if the first problem is NP complete, right, then the second problem is also NP complete. Okay, so this is why it's very useful to have these NP complete to study these reductions. Okay, because now you can just go from one NP complete problem, and then you can sort of expand that into more NP complete problems as long as you can prove these reductions. Okay. So in fact, there are many NP complete problems. Okay, so people have proved many of these reductions, and so there are like thousands of NP complete problems. Okay. And they're related to each other via this this sort of web of interconnections of reductions. Okay. Any questions about this? Okay. So all right. So let me sort of prove more formally what I said earlier. Okay, which is that if you have two NP complete problems A and B, and if A is NP complete, and if A reduces to B, then B is also NP complete. Okay, poly time reduces to B. Okay, then B is also NP complete. Okay, so let's prove that. Okay, so what we have is that if you have any other problem C, so C can be any NP problem. Okay, then because A is NP complete, C will reduce in poly time to A. Okay, and because A reduces to B in polynomial time. Okay, because this is our assumption. Okay. Then we can use the previous theorem about composing these polytime reductions. Okay. Then we can say that C reduces to A, which reduces to B, and so that implies that C polytime reduces to B. Okay. And because this holds for any NP problem, okay, so this means that any NP problem polytime reduces to B. Okay. And furthermore, we assume that B itself is an NP. And so that means that B is now NP complete. Okay, so that's the proof of this fact. Okay, so now to make use of this theorem, what we can say is that so oftentimes we want to show that a problem is NP complete. Okay, then in order to do this, you can take some other problem A, and if you know that A is NP complete, and if you can prove that A polytime reduces to B, then this shows that B is NP complete. Okay. And so A can be any NP complete problem. Okay, the nice thing is that you don't have to pick some particular problem. You can pick any problem you want. Okay, and as long as you can prove this reduction, and in order to prove this, you actually need to give a polynomial time reduction from A to B. And sometimes this is kind of hard to do. Okay, but as long as you can come up with this reduction, and then also you need to prove that B itself is an NP. Okay, but usually that's not so hard to do. But once you do these two steps, then this shows that B is NP complete. Okay, so any questions about this? Okay, so I'm just going to say a few more things before we take a short break. Okay, so the next thing is I said that NP complete is a very useful class of problems to study this P versus NP problem. Okay, and so now we're going to see why. Okay, and so suppose you have a problem A which is NP complete, and suppose you can somehow show that A is also in P. Okay, so suppose you found one of these very hard NP problems, and you also found a polynomial time algorithm for this problem. Okay, then you've proven that P equals NP. Okay, so if you can do this step, okay, then you've proven that P equals NP. Okay, and then you solve that very famous problem, and now you're very famous too. Okay, and so the proof of this fact is that if you take any other NP problem B, okay, then if A is in P, then we can show that B, which is any other NP problem, is also in P. Okay, and the reason is that because A is NP complete, then there's a polynomial time reduction from B to A. Right? That's the definition of A being NP complete. So now if I give you an instance x of B, right, then I can just run this polynomial time reduction to transform x to an instance of A. And since you've proven that A is solvable in polynomial time, right, then I can just solve this instance of A in polynomial time, right? And the answer tells me, that gives me the answer for this instance x of B. Okay, right? So I take this instance of B, I transform it to an instance of A, right? I use my polynomial time algorithm for A, and now I get the answer for B. Okay, and because this holds for any NP problem, then this shows that any NP problem can be solved in polynomial time, right? Because this reduction here runs in polynomial time, and this A algorithm also runs in polynomial time. So therefore the overall algorithm runs in polynomial time. Okay. Okay. Right. So that's what I said. Okay. Yeah. So that's the first thing. Okay, is that if you can show any NP complete problem is in P, then you've shown that P equals NP. Okay. Now, on the other hand, if you can show that any NP complete problem is not in P, okay, then for any other NP complete problem, this problem is also not in P. Okay, because we can prove this by contradiction. Okay, because if this other NP complete problem, if B is in P, okay, then because B is NP complete, then by the previous theorem, we have that P equals NP. Okay, and so because A here is an NP problem, right? A is an NP complete problem, so it's also an NP problem. Okay, and so A is an NP problem, and because P equals NP by the previous theorem, then A would also be in P, which contradicts our assumption here. Okay. So if you can show that any NP complete problem is not in P, then you've proven that all NP complete problems are not in P. Okay? Yeah, so basically, so now, suppose you want to prove that P is not equal to NP. Okay, that's what most people think. P is not equal to NP. Then it's enough to show that one NP complete problem is not solvable in polynomial time. Okay, using this corollary. Because if you show any NP complete problem is not in P, then you've shown that all NP complete problems are not in P. And that shows that P is not equal to NP. Okay. Now, unfortunately, we currently don't have any proofs of this. Okay, so even though you're allowed to pick any NP complete problem you want, and so the nice thing about being allowed to pick any NP complete problem is that there are many NP complete problems, right? If you go back to this chart, okay, so you can pick whichever problem you think is like the easiest to work with, Okay, so maybe you're very good at like logic problems. Okay, so maybe you want to pick like SAT as the problem that you want to focus on. Okay, or maybe you're good at like, let's say, combinatorics. Okay, so maybe you want to pick subset sum. Okay, or maybe you're good at graph algorithms, so you want to pick TSP, traveling salesman. Okay, so you can pick any NP complete problem to start with, and if you can show that your problem is not NP, then that would show that all NP complete problems are not NP. Okay, so you have lots of flexibility. However, even though you have this flexibility, and people have been trying to do this for like 50 years, nobody has succeeded up to now. Okay, so nobody has shown a nobody has given a polynomial time algorithm for any NP complete problem, or shown that an NP complete problem cannot be solved in polynomial time. Okay, so this is why we still don't know the answer to whether P equals NP. Okay, any questions about this? Okay, all right, so we're gonna take a short break. Let's take a 5-minute break to something like, what time is it? To like 11:07. Okay, so let's try to come back in 5 minutes, and then I'll continue with this. Okay, all right, and if you have any questions, please type it out in the chat box. Okay, so somebody's asking, we define what decision problems P is defined without the constraint. Uh, Okay, let me just say the answer to this. Yeah, so somebody's asking if y equals f of x and you solved y, do you need to transform y back to a solution for x? So you do not need to do that, okay, because we're only considering decision problems right now. Okay, so x either is a yes instance or a no instance. Okay, yeah, so the answer to x is either yes or no, and the answer to y is also yes or no. Okay, so if y has a yes answer, x has a yes answer. If y has a no answer, x also has a no answer. Okay, yeah. So somebody else was also asking about, can you define P versus NP for problems which are not decision problems, right? So what if I actually want to find the solution? Like if I give you a factoring problem, okay, I'm not just asking whether it has a non-trivial factor, but I actually want to find a factor. Okay, so that's So NP is usually defined only for decision problems, but there's another class called I think it's called FMP. I think it's called like function MP. Okay, and those are defined for like non-decision problems where you actually want to find the answer. Okay. So I don't know the formal definition off the top of my head, but it's basically the same idea as for the MP definition. And also, if you can solve the decision version of a problem, you can oftentimes also solve the so the other version where you have to find the answer. That's usually called the search version of the problem because you actually have to find the answer. Okay, and so if you can solve the decision version of a problem, you can usually also solve the search version of a problem. Okay. So for example, suppose I'm trying to factor a number. Okay, so I can convert that to a decision version where I can say, is there a factor of this number which is less than some amount? Okay, which is less than, let's say, so let's say I'm trying to factor 1,000,000. Okay, so I can ask, is there a factor less than 1,000? Okay, or not 1,000. Is there a factor less than, let's say, 10? Okay, is there a factor less than 20? Is there a factor less than 40, 80, 160, and so on? Okay. So each of those things is a decision problem, right? Because it's either yes or no that there's a factor less than 10 or 20 or 40 or whatever. Okay. But if I can answer all of these questions, then I can basically use some sort of binary search approach to actually find a factor. Okay, because if there is a factor, yeah, I can basically use some sort of binary search to actually find that factor. And so as long as I can answer the decision version of this problem, right, then I can also, in many cases, answer the search version of the problem. Okay, so that's why the search version of NP problems and the decision versions are kind of like equivalent to each other. Okay, I'm not making like a mathematically rigorous statement here. Okay, it's just sort of like an intuitive statement. Okay, but that's the basic idea. Okay, any other questions? Okay, so let me just say a few more things about this NP, and then after that, we'll actually do one of these reductions. Okay, so we'll actually prove some other other problem is NP complete. Okay, so just a few more things. So NP, it's a very large set of problems. Okay, it contains many important practical problems. However, not all problems are in NP. Okay, not all interesting CS problems are in NP. Okay, so as an example of this, suppose we look at this graph isomorphism problem. Okay, so here what happens is I give you two graphs, right? Like I give you the top graph and then the bottom graph. Okay. And then the question is, are they isomorphic to each other or not? And what I mean by isomorphic is that suppose, so these two graphs don't look like each other, right? Like visually, they don't look like each other. Okay. However, if you take the top graph, okay, so you notice that all the vertices have colors. Okay. And then if you map them onto the bottom graph, where the same color goes to the same node, right? Like, blue goes to blue and green goes to green. Okay. Then what you can see is that whenever you have an edge between two nodes on the top graph, right, like the blue and the green are connected in the top graph, and they're also connected in the bottom graph, right? like for example, the yellow, okay, and this orange, right? They're connected in the top graph, and they're connected in the bottom graph. Okay, so this means that it's possible to take the 8 vertices in the top graph and then map them to the 8 vertices in the bottom graph, and you can preserve all of the edge relationships with this mapping. Okay, so the mapping I'm going to call F here, right? It maps from the first graph to the second graph, and it preserves all of the edges. Okay, the edge relationships. So in this case, we say that these two graphs are isomorphic, right? They look like each other. Okay. All right, so this graph isomorphism problem is the yes instances are all the graphs which are, all pairs of graphs which are isomorphic to each other. And the no instances are all the graphs, are all pairs of graphs which are not isomorphic to each other. Okay. So now you can show that this problem is an NP. Because in order to show that you have a yes instance, you just need to provide this mapping. Okay, and this mapping is actually pretty simple, right? It's just you can express it in polynomial time. Okay. All right. However, now you can transform this graph isomorphism problem to graph non-isomorphism. Okay, so graph non-isomorphism is exactly opposite of graph isomorphism. Okay, so now when you have two graphs which are isomorphic, right, then in this graph non-iso problem, this is a no instance. Okay, so graph non-isomorphism is looking at when are two graphs not isomorphic to each other. Okay, so these two graphs would be a no instance of graph non-isomorphism. Okay, whereas for example, these two graphs, right? Let's draw them like this, right? These two graphs would be a yes instance of graph non-isomorphism because they're not isomorphic to each other. Okay, yeah, so graph non-isomorphism is the opposite of graph isomorphism. Okay, however, the thing is that we don't know whether graph non-isomorphism is an NP. Okay, even though we know the opposite of this problem is an NP, we don't know whether this, when you flip the problem around, we don't know whether this problem is an NP or not. Okay, and sort of the intuitive reason for this is that suppose I give you two graphs, okay, and suppose they're not isomorphic to each other. Okay. Then how do you produce a short certificate which proves that these two graphs are not isomorphic? Right? Like if you want to prove they're isomorphic, you just give this mapping, right? Blue to blue, green to green, and so on. Right? So that's a very short proof that these two graphs are isomorphic. But if you want to prove that they're not isomorphic, like how would you do this? Okay, like one thing you could do is you can give like a bunch of possible mappings, and you can show that each of these mappings fails. Okay, right. However, you need to give like in order to show that two graphs are not isomorphic, you need to show that they're not isomorphic under any mapping. So if you have n nodes in the graphs, right, there are n factorial different ways to map one graph to the other, and you have to show that all of these mappings fail. Okay, so how would you express this fact succinctly? Okay, because you cannot just list out all of these relabelings and say that each one of them fails, because there are an exponential number of these relabelings. Okay, so we need a polynomial time verifier. If you want to show that graph non-isomorphism is an NP, you need a polynomial time verifier. Okay, so that polytime verifier cannot check all of these exponential number of labelings. So this is why it's hard to show that graph non-isomorphism is an NP. Okay. Yeah, and also we don't know of a polytime algorithm to solve this graph non-isomorphism problem. Okay, so this is an example of a problem which we don't know whether it's an NP or not. Okay, so so in fact, this graph non-isomorphism, okay, this belongs to another class of problems called co-NP. Okay, co stands for complementary, complement. Okay, it's like whenever you have one problem which is an NP, if you flip that problem, so all the yes instances of the first of this NP problem become no instances of the co-NP problem, right? And all the no instances become yes instances. Okay, so you flip this problem. Then if the original problem is an NP, then the new problem is in co-NP. Okay, so co-NP is another set of problems. Okay, and each of these sets is called a complexity class. Okay, So P is a complexity class, NP is a complexity class, and so there are many, many complexity classes. Okay, so there's another one which we'll talk about later called P space. Okay, that's also a set of problems, and this is like all problems which you can solve in a polynomial amount of space. Okay, right. So P is all the problems you can solve in polynomial time, and P space is all the problems you can solve in polynomial space. Okay, yeah. So it turns out that all problems in P also belong to P space. Okay, so whenever you can solve a problem in polynomial time, you can also solve it in polynomial space. Okay, so we'll talk about that later. All right, but another complexity class is exp time. Okay, so this stands for exponential time. So this is all the problems which you can solve in exponential amount of time. Okay, and it turns out that this includes all of the problems in P and NP. Okay, so even these NP problems, you can always solve them in exponential time. Okay, and now this exp time, there's actually a non-deterministic version of this. Okay, which is called n-exp time. Okay, and so this sort of the relationship between these two classes is like the relationship between P and NP. Okay, so n-exp time is all of the problems whose where a correct answer can be verified in at most exponential time. Okay, so exp time is we need to solve the problem in exponential time. And n-exp time is where you need to verify a correct answer in exponential time. Okay? All right, so I'm just listing out a bunch of complexity classes. I'm not going through any of them in any detail. Okay, so this so there's a huge field of study devoted to these complexity classes called complexity theory. Okay, so you can easily have many classes on complexity theory. Okay, so it's a very interesting and rich field, and actually I don't know that much about it. Okay, so all I'm doing over here is just listing out a bunch of commonly used complexity classes. Okay, so yeah, so each of these things is called a complexity class, and there are many, many other complexity classes. Okay, so in fact, there's this very nice website which has a set of many complexity classes which you can look at. Okay, yeah. So for the by the way, I found that the old version of the slides had an incorrect URL. Okay, so that URL doesn't work anymore. So I changed it to the correct URL in this slide. Okay, so the final thing I'll say is that the study of complexity classes is called complexity theory. Okay, and complexity theory basically wants to figure out the relationships between these classes. Okay, so so here in this picture, what I did is I drew a bunch of complexity classes. Okay, for example, you have P over here, you have NP over here, right? You have co-NP, and so on. And so each of these complexity class is a set. Okay, so I'm drawing them in this Venn diagram form, where if you have one thing which is contained in another, then this means that the first set, right, this A set is a subset of B. Okay. However, in many of these cases, we don't know whether it's a strict subset. Okay, we don't know whether A is strictly contained in B, right, meaning that A is smaller than B, or maybe A is just maybe A is equal to B. Okay, for many of these many of these relationships in this diagram, we don't know whether it's a strict containment or not. Okay. In fact, we don't know that much about this diagram. Okay, all we know are some pretty, I would say, basic things. Okay, so for example, we know that P is a subset of NP. Okay, we know that NP is a subset of exponential time. Okay, and we know some sort of non-trivial things also. Okay, so we know that, for example, there's this the P space class is actually equal to NP space, which I'm not going to define. Okay, and then there's this other class called IP. Okay, so these are all equal to each other. Okay, and then we also know that this other class NL is equal to co-NL. Okay, so all of these results are very are highly non-trivial results. Okay, they're very difficult to prove. Okay, however, we don't have many of these results. Okay, because there are many, many possible relationships in this diagram, and we actually only know a few of these relationships. Okay, yeah. So for example, things that we don't know are, is P equal to NP? Okay, we don't know that. Okay, is P equal to co-NP? Is NP equal to co-NP? Okay, is NP equal to P space? Okay, so many of these things we actually do not know. Okay, and and we haven't made too much progress either. Okay, it could be we're using the wrong methods or something. Okay, but if we can figure out any of these relationships, this would actually have a lot of very important implications for both computer science and also just sort of many other branches of science and mathematics. Okay, so this is why complexity theory is a very important but also very difficult field of study. Okay, so that's all I have to say about this introduction part. Any questions? Okay, so then next we're going to move on to the next lecture, which is going to be, where's this? Oops. Yeah, okay, so next we're going to actually look at how to do some of these NP completeness proofs. Okay, we're going to look at how to construct these reductions in order to show certain problems are NP complete. Okay, so we'll just do this by using a bunch of examples, okay, because each of these proofs is quite different from each other, and it requires a lot of thought. Okay, so there's sort of no sort of systematic way to come up with these proofs. Okay, so the best way to show how you do them is just to look at a bunch of examples. And then through these examples, you can get some sort of, you can find some maybe patterns or methodologies. Okay, so the first problem we're going to show is NP complete is this clique problem. Okay, so we talked about the k-clique problem, which is that I give you a graph, and then you have to find k nodes which are connected. Okay, so the clique problem is very similar, except for here, if I give you a graph with n nodes, I just want to find a clique with n divided by 3 nodes. Okay, with exactly n divided by 3 nodes. Okay, so k-clique, I can allow any k, but here I just allow, I'm required to find a clique with 1/3 of the nodes. Right. Okay, so first of all, you can show that clique is an NP, okay, because we saw that k-clique is an NP, so clique is also in NP. Okay, so so the certificate is just if you give me a graph with n nodes, the certificate would just be n divided by 3 nodes, which do form a clique. Okay. All right, so this is pretty easy. Okay, so the hard part is to show that all NP problems reduce to clique. And so we're not going to do it this way. Okay, so if you want to prove clique is NP complete directly, you would have to show that all NP problems reduce to clique. Okay, and that's hard because there are many NP problems. So instead, we're going to do it the indirect way, which we just talked about, which is that we're going to take some other NP complete problem, okay, and we're going to reduce it to clique. So we proved a theorem which said that if any NP complete problem reduces to clique, then clique is also NP complete. Okay, and then notice that the problem you choose has to be NP complete. Okay, it cannot just be like an NP problem, right? It has to be one of these hardest problems from NP. Right, and the other thing you have to be careful about is that you're reducing this NP complete problem to clique. Okay, you're not trying to reduce clique to some NP complete problem. Okay? If you did that, that actually wouldn't prove that clique is NP complete. Okay, because that would just prove that clique reduces to some other very hard problem. Right, that would show that clique is solvable using some other very hard problem. But that doesn't imply that clique itself is hard. Right? I mean, it might be that clique is very easy, but you can transform it to this hard problem. Okay? So you cannot prove, so if you want to prove clique is NP complete, you cannot prove that clique reduces to an NP complete problem. Okay? You have to show that an NP complete problem reduces to clique. Okay, so just be careful about that because it's kind of easy to sort of make that mistake. Okay, and the final thing is that we can actually choose any NP complete problem to reduce from. Okay, any one that you want. Okay. And so you have to choose the right problem. Okay? Because if you choose a wrong problem to reduce from, then it can make the reduction very hard to construct. Okay? But if you choose the right problem, then it makes it easier to come up with these reductions. Okay? And so this is so when you do one of these proofs, oftentimes one of these hard steps is to think about which NP complete problem do I want to reduce from. Okay, yeah, that's important. Okay, so now for our problem, right, the problem we're going to reduce from is going to be called 3CNF sat. Okay, so this is another one of these Boolean satisfiability problems. Okay, except for it's got a very special form. Okay, so 3CNF sat, the formulas have to have the special form where they're basically a bunch of ands. Okay, so we're anding together a bunch of these things. Each of these things is called a clause. Okay, so the clause always has 3 variables in it. Okay, and these variables are called literals. Okay? So the literals can either be positive literals, like this A is a positive literal, or they can be like negative literals. Okay, so this not C, right? This would be like a negative literal. Okay, but each of these things, so this is called a clause. Oops. Okay, and then each clause has to have 3 literals in it. And the literals are always ORed with each other. Okay? All right, so then when we have a bunch of these clauses, and then we AND together all of these clauses. That is a 3CNF formula. Okay? So a 3CNF formula is an AND of ORs of 3 literals. Okay, it's an AND of ORs of 3 literals. Okay, and the 3CNF sat problem is saying that if I give you a 3CNF formula, is it satisfiable? Okay, so for example, if I give you this formula, is there a way to set these Boolean variables to satisfy this, this formula? Okay, and in this case, it is satisfiable. Okay, because for example, you can set A, B, and C to true, and you can set D to false, and then this makes the entire formula true. So this is a satisfiable instance of 3CNF sat. Okay. Yeah, and it turns out that even though we're restricting this formula to this very special form, right, this AND of ORs of 3 literals, okay, it turns out that, you know, if I give you any sat formula, I can always transform it to another 3CNF sat formula, which is about the same size as the original formula. Okay, so we're actually not losing any generality by considering these special forms of the formulas. Right, now it's actually known that 3CNF sat is NP complete. Okay, so therefore we're going to assume that 3CNF sat is NP complete, and we're going to reduce 3CNF sat to clique in order to show that clique is NP complete. Okay, so just to remind you, so if we have this reduction, then what this would mean is that if you start with a formula phi, okay, then in polynomial time, you can create a graph G such that the formula is satisfiable if and only if the graph has an n/3 clique, where n is the number of nodes in the graph. Okay. Right, so this is actually kind of the first time that you see this, it might be kind of like a bizarre statement, okay? Because what we're doing is we're relating this formula phi to a graph, okay? And it seems like, you know, formulas and graphs don't really have anything to do with each other, right? So a priori, if you give me a formula, right, I'm going to think of it as simply as a formula. It's hard to think of this in any other way. But somehow, through this reduction, you can transform that formula to a graph, and the formula and the graph are very related to each other. Okay, because the formula is satisfiable if and only if the graph has an n/3 clique. Okay, all right. So to do this, we're going to have to construct a very special graph. Right? It's not just any graph that's going to work. We have to construct this graph in a very special way, and this is going to be our reduction. Okay, so the way we're going to do this reduction is, suppose you start with a formula. Okay, so it's a 3CNF formula, and suppose it's got m clauses. Okay, then what you're going to do is take any clause in this formula. Okay, so that clause has 3 literals. Okay, so now in our graph, so we're going to make a graph, right? So we're going to make 3 vertices corresponding to these 3 literals. Okay. All right, so that means that if you have m clauses in total, then each clause is going to have 3 literals, and so and that produces 3 vertices. So in total, our graph is going to have 3 times m number of vertices. Okay, right? And then let's let n be the number of nodes in the graph. And so now we're trying to find a clique with size 1/3 of the number of nodes. Okay, so therefore we're trying to find a clique of size m, right? N here is equal to 3m, and so we're trying to find a clique with 1/3 of the nodes, which is m nodes. Okay, so those are all of the nodes in the graph. Okay, so now we need to say what the edges are. Okay, so now suppose you have two nodes in the graph, u and v. Okay, then we're going to add an edge between these two nodes if we have the following two conditions. Okay, so first of all, u and v, right? Well, they come from these clauses, right? Because what we do is you start from a clause and then you form these vertices. Okay, so each vertex comes from a clause. So we're going to make an edge between u and v if they come from different clauses. If they come from the same clause, we do not put an edge between u and v. Okay, so the next condition is that u and v also cannot be negations of each other. Okay, so for example, if u is equal to the variable x1, let's say, then v cannot be not x1. Okay, if u is x1 and v is not x1, then we do not put an edge between these two nodes. Okay, yeah, so when they're not negations of each other, we say that u and v are consistent with each other. Okay, so let's do an example of this. Okay, so an example would be you start with this formula phi over here. Okay, right. So now for each clause, right? So we have three clauses. Okay, for each clause, we're going to make three nodes. Okay, so for example, for the first clause, we're going to make three nodes. Okay, we have x1, not x2, and not x3. Right? And we're going to label them this way. And likewise for the second clause, right, which is we're going to make three nodes. Okay, exactly corresponding to the literals. Okay, so therefore in total we're going to have 9 nodes. Okay, so next we need to create the edges between the nodes. Okay? And the two conditions are that first of all, for all of these nodes, they all come from the same clause. Okay, so therefore we do not put any edges between them. Okay, likewise these nodes, they also come from the same clause, so you do not put edges between them. Okay. Right, so that's the first condition. And then the other condition is that you do not put edges between nodes which are negations of each other. Okay, so for example, these two nodes, right? They come from different clauses, but they're negations of each other, so you don't put an edge between them. Okay. On the other hand, if you take these two nodes, right? Well, they come from different clauses, and they are not negations of each other, so you do put an edge between them. Okay, so for any nodes which do not violate these two properties that we have, okay, so as long as the nodes come from different clauses and they are not negations of each other, then you are going to put an edge between them. Okay, so as another example, if you take x1 and this x2 here and x1, right? Well, they come from different clauses and they're not negations of each other, so there's an edge. However, this x2 and this not x2, okay, they're from different clauses, but they are negations of each other, so there is no edge between them. Okay, so this is how you create all of the edges. Any questions about this? Okay, so now we've converted this initial formula to this special graph, right? And the claim is that this special graph is going to have a clique. It's going to have an m clique. So this graph has 3 times m number of nodes. Okay, and the claim is that this graph is going to have an m clique, if and only if the initial formula is satisfiable. Okay, that's what we're going to prove. Okay, now before that, we need to show that, so we did this reduction from this formula to this graph. Okay, now one requirement for this reduction is that it has to run in polynomial time, right? And so we have to show that our construction runs in polynomial time, but this is true because in order to convert this formula to this graph, right, you just basically go through this entire formula over here, okay? And then you have to add all of these edges. So potentially there are like order n squared edges. Okay, so this this construction takes you order n squared time to run. Okay, so therefore this is a polynomial time reduction. Okay, but next we have to show that if you start with a satisfiable formula, okay, then the graph you produce has an M clique, right? If and only if. Okay. All right, so we have to show both directions. Okay, if you have a satisfying assignment, then it's got an M clique, and if it's got an M clique, then the original formula is satisfiable. Okay, so we have to show both directions here. Okay, so let's show the first direction, okay, which is that suppose there does exist a satisfying assignment to the formula. Okay, then we're going to show that there exists an M clique. Okay, all right. Now the reason for this is that I guess, yeah, let's go back to this one. Okay, yeah. So if you have one of these formulas, okay, then the thing about then how can you satisfy this formula? Well, this formula is it's an AND of a bunch of clauses, right? Okay, so therefore, in order to satisfy this formula, you have to satisfy every clause, right? Every clause has to be true, because otherwise, when you AND them together, you don't get true. Okay, right? So if every clause is true, then because every clause is an OR of the literals, then at least one of these literals has to be true, right? Because if all three literals in a clause are false, then the entire clause is false. And if you have a false clause, then when you AND it with the other clauses, the result is going to be false. Okay? So in order to satisfy this formula phi, you need to somehow pick a true literal from every clause. Okay, and so this is a necessary and sufficient condition to solve this phi. Okay. All right. So yeah. So therefore, for each clause, we can pick out a true literal, right? Because we're assuming that there is a satisfying assignment, and if you use that assignment, okay, then it must be that using this assignment, every clause has a true literal. Okay, and so because you have M clauses, then you've picked out M literals, okay, where M is equal to N divided by 3. Okay, now each true literal that you picked out, okay, it corresponds to a vertex in the graph, right? Because that's how you build the graph, okay? For every literal, you create a node in the graph, okay? So for all of the literals that you picked out, all of these true literals, okay, you're gonna pick out the corresponding vertices from the graph, okay? So that's gonna be M vertices in total. And the claim is that these M vertices are all connected to each other. So they form an M clique. Okay, that's the claim. Okay, so why is this true? Okay, so suppose you take any two vertices that you selected. Okay, okay. Now, first of all, U and V, they come from different triples of vertices, right? So remember that you have these triples of vertices. Okay, so these U and V, right? They have to come from different triples because each literal comes from a different clause. Okay. And the vertex that you select corresponds to one of these literals. Okay, so therefore U and V are going to come from different triples of vertices. Okay, and second, we have that U and V are consistent. Okay, in other words, they are not negations of each other. Okay, and the reason they're not negations of each other is because when we picked out these literals, right, you only picked true literals. So therefore, if these two literals are negations of each other, right? So for example, let's say that you have this literal U over here, and then you have not U over here. Okay? Then it cannot be that both U and not U are both true. But all of the literals that you picked are true literals. Okay? So therefore, they cannot be negations of each other, because if they were, they cannot be both true. Yeah, okay, so we have that these literals that you pick, first of all, they come from different triples, and they're not negations of each other. So therefore, by the way we constructed the graph, we put an edge between these two vertices. Because you put edges between any vertices which come from different triples and which are not negations of each other. Okay? Yeah. Okay, so as an example of this, right, and so, oops. Okay, so this shows that for any two vertices that you picked, those two vertices are connected to each other. Okay, And so because in total we picked m vertices, right? We picked m vertices in total, then this shows that any pair of these m vertices is connected to each other. And this shows that these m vertices form an m clique. Okay, so whenever you have a satisfying assignment, then you have these true, you have at least one true literal for each clause, and so you can pick out these m vertices corresponding to these true literals, and we prove that these m vertices are all connected to each other, and they form a clique. So therefore, we've shown this statement up here. Okay, now as a sort of a concrete example of this, okay, so we have this formula. This is a satisfiable formula, okay, and one way to satisfy it is to just set x1, x2, x3 all to be true. Okay, you see that if you set it to be true, right, then the first clause is going to be true, right? The second clause is going to be true, right, and the third clause is going to be true. Oops. Okay, so now you know, the way that so now we can use this satisfying assignment to find a 3 clique. Okay, so the way that we find it is for each of these clauses, we're going to pick out a true literal. Okay, so for clause 1, we're going to pick out this literal because x1 is true. Right. For clause 2, we're going to pick out this one over here. Okay, this is also true. Okay, and for clause 3, right, we set x3 to be true, so we can pick this as our vertex. Okay, and now we have that these 3 vertices form a 3 clique. Okay, because indeed you can see that they are all connected to each other. Okay, and why are they connected? Because, you know, x1 and x2, right, they come from different triples, and they're not negations of each other. So therefore we connect them. Okay, x1 and x3, right, they also are not negations of each other, so we connect them. Okay, and they come from different triples. Okay, so in fact, for any satisfying assignment, okay, this works. Okay, so let's do one more example. So let's say that, you know, if you want to satisfy this, let's say we're going to make this to be, let's say we're going to make this to be true. Okay, so then we're going to make this to be true. And then we're going to make, let's say, which one? Okay, then we have to make this one be true. Okay, oops. All right. Okay, so this is also a satisfying assignment, right? So our assignment is going to be x2 is going to be false. Okay, so therefore not x2 is going to be true. Okay, x1 is also going to be false, so not x1 is true, and x3 is going to be true. Okay, so we claim that this also corresponds to a 3 clique. Okay, because for example, in this graph over here, you have not x2, right? This thing is true, right? For the second clause, you have not x1, okay, this one, and then for the third one, you have x3, okay? And you can see that these 3 nodes are connected to each other. Okay, so we see that anytime you find a satisfying assignment in this formula, right? If you pick out these corresponding nodes, then they're going to form an M clique in the graph. Okay, any questions about this? Okay, now, okay, so then next we're going to do the other part, okay, because we need this reduction to be if and only if. So now we need to show that if there is an M clique in this graph, okay, then there is a satisfying assignment to the formula. Okay, and the reason this is true is because suppose you have an M clique, okay, so let's pick out these M vertices, which are all connected. Right, so now the first thing is that because these vertices are all connected, okay, they cannot correspond to literals from the same clause, right? Because, you know, if you take the 3 literals from the same clause, then they're not connected to each other by our construction, right? Like our construction never connects literals within the same clause. And so because you have M vertices and all of these are connected to each other, then they cannot correspond to literals from the same clause. So yeah, so in fact, because you have M vertices, these M vertices have to correspond to literals from different clauses. And since you have M clauses in total, then this means that you have one vertex from each clause, right? So each of these, sorry, let me say it again. Okay, each of these vertices corresponds to a literal from a different clause. And so in total, these m vertices correspond to m different literals, all from different clauses. Okay? Right. And next, so basically this means that, if you take these m vertices, then this allows you to pick out one literal from each clause. Okay? Right. So that's the first property. The second property is that none of these vertices that you pick, none of them correspond to a literal and its negation. Okay, so if you pick two vertices, u and v, okay, it cannot be that, for example, u corresponds to, let's say, x1, and then v corresponds to not x1. Okay, that cannot be. Okay, and the reason simply is that we know that u and v are connected to each other because they're in the clique. Okay, and we never put edges between negations, between negated variables, negated literals. Okay, so therefore, u and v do not correspond to a literal and its negation. Okay, right. So basically, we've now so from these m vertices, right, this produces m literals. Okay, these m literals, they all come from different clauses, and they're not negations of each other. Okay, and now we're going to take all of these literals and we're going to set them to be true. Okay, and we claim that this assignment, where we set all of the literals that we picked out to be true, this is going to be a satisfying assignment. Okay, and why is this the case? Well, it's because these m literals come from different, all come from different clauses, right? So that means that we have one literal per clause, and we set that literal to be true. Okay, so now we have one true literal per clause, and so now all of the clauses are true. Okay, and furthermore, because these literals that we picked are not negations of each other, this is a valid assignment. Okay, so what I mean by that is, suppose you picked out two literals. Okay, suppose you picked out x1 and not x1, and you want to set both of them to be true. Okay, well, this is invalid. Right? You cannot set x1 and not x1 both to be true. Okay? But we know that for these literals that we picked, right, we never pick a literal and its negation. Okay, I mean, you can pick x1 and let's say not x2, right, and you can set both of them to be true. Okay, there's no contradiction in that. Okay, so all of the literals that we pick are not negations of each other, so it is valid to set all of them to be true. Okay, and because each node corresponds to one literal from a different clause, then we have one true literal per clause. Right? We have one true literal per clause, so every clause is true. And so when you take the AND of all these clauses, you get a true, you get a satisfying assignment. Okay, so this shows that when you have an M clique, right, you can use it to produce a satisfying assignment. Okay, so let's do an example of this also. All right, so let's take an M clique in this graph. Okay, so any clique that we want, let's say we, what do we have here? All right, let's say, which ones? I guess not any one. All right, so let's pick these three nodes. Okay, right. So these guys form a clique, right? And what we're saying in this construction is that we're going to set all of these literals to be true. Oh, well, so this just corresponds to what the first one I started with. Okay, yeah. So anyways, let's do it. Okay, so let's set this to be true. Let's set that to be true, and let's set that to be true. Okay. So now you can see that this clique that we found. First of all, each literal comes from a different clause. Right? Like x1 comes from clause 1, x2 comes from clause 2, and x3 comes from clause 3. Okay. So now we've chosen one literal per clause. Okay. And furthermore, these things are not negations of each other. Right? Like x1, x2, x3, they're all not negations of each other. Okay. So therefore, it is possible to set all of them to be true simultaneously. And when you do that, right, if you do that, then you get that this entire formula is true. Okay, so let's do another example. Let's find some other clique. That's not, I guess not. So, okay, let's find this clique. Okay, All right. So here again, you see that these vertices come from different clauses. Okay, and let's set all of them to be true, and you can see that they're not negations of each other. Okay, so it's possible to set all of them to be true, and when you do this, you have that not x3 here is going to be true, right? You have not x1 is going to be true, oops, right? And then you have x2 is going to be true, okay? And so altogether, this makes the entire formula be true. Okay? So therefore, you've gone from an M-clique to a satisfying assignment. Okay? And we also showed that you can produce a satisfying assignment from an M-clique. Right. So therefore, we've shown both directions of this reduction, and this shows that 3CNF-SAT reduces to clique. Okay, and that shows, and because we know clique is in NP, this shows that clique is NP complete.